Can you imagine this rocket rising not just into the sky, but beyond gravity's reach? You see, every second it is climbing, it's working against Earth's pull, and you could say it is buying its freedom with energy. But how much energy does it take to break free? That is, to escape not just Earth, but gravity itself and go into infinity. Well, physicists have found that and have wrapped the answer into one elegant formula, that is, gravitational potential energy U is equal to minus gmm upon r. And in next few minutes, we will uncover what this truly means. So, up until now, whenever we needed to calculate the potential energy of a particle, we would invariably take the particle, say a ball, at a height h above the Earth and use the formula mgh to determine its potential energy. And in doing so, we made a reference choice where at Earth's surface, the h value was considered 0, and therefore the potential energy was also 0. And this potential energy increased as the separation between the Earth and the object increased. Now, notice that any such particle was almost always considered near the Earth's surface, usually just a few meters above or at the most a couple of kilometers. We never really considered extreme scenarios like an object positioned 100,000 kilometers away from Earth, which basically meant that the g value did not change much at all. And for all practical purposes, we could take it as 9.8 meters per second square. In other words, we could consider the gravitational force constant near the Earth's surface and given as gmm upon r square. That is nothing but mg, because if you calculate this part, that is gm upon r square, it becomes 9.8 meters per second square. But now we wish to go beyond a few kilometers and find the potential energy of any two masses separated by a distance r that could be interplanetary and span several 100,000 kilometers. In such cases, the simpler formula U is equal to mgh no longer holds because g is no longer constant. Instead, we rely on a more general and universally applicable formula derived from Newton's law of gravitation. So, the potential energy of two particles separated by a distance r is given by the formula minus gmm upon r. Now, this formula needs a bit of attention to fully grasp it, and then you can use it effectively while solving problems. But before we do that, a few things. Number one is that you need to remember that potential energy is a property of a system of the two particles. That is, it is not attributable to one particle alone. So here, when we say that the potential energy of the system is this expression, basically it is the potential energy that belongs both to m and this m collectively. However, we can take some liberties if this m is much larger than this m, like we have the Earth and ball system here. So in such cases, we take the potential energy as if it belongs to the ball alone, even though it belongs to both Earth and the ball. Now, we can make this assumption here because you see, when the ball moves up or down, whatever change happens in the potential energy, it is that of the ball and not of the Earth. That is, we do not see the Earth moving up or down, and so its potential energy hardly changes. This can also be understood from the viewpoint of change in kinetic energy of each participant in the system. So we see here that kinetic energy of the ball changing as the separation increases or decreases, while the kinetic energy of Earth does not change, or more accurately changes to an almost immeasurably small extent. So this change in kinetic energy that happens largely in the ball shows up as the change in its potential energy as well in accordance with the law of conservation of energy. Now, if we take a satellite orbiting the Earth, all that we've discussed for the ball would hold true for the satellite as well, simply because its mass too is much smaller than that of Earth. Okay, now when we talk about the potential energy of bodies that have comparable masses, say Moon and Earth, we need to be careful and consider the calculated potential energy as that of the system rather than attributing to one mass. Now, memorizing this formula can help you crack most physics problems. However, if you're faced with a tricky problem on this topic, you would probably struggle. So, to enable you to tackle tough problems, it is important that you understand the derivation of this formula. Because the derivation doesn't just give you the mathematical steps, it also reveals the physical meaning behind the equation, builds intuition, and helps you apply it a lot more confidently. Okay, so let us project a ball straight up from Earth like this. And here we're interested in finding an expression that can help us calculate the potential energy at a point Q in its path. And let us say this point is at a radial distance r from the Earth's center. So you would have noted that I did not say that we should calculate the potential energy of the ball, because this expression, as we discussed earlier, strictly speaking, is the potential energy of the system, that is Earth and ball separated by a distance r. Now, when we dealt with particles near the Earth, we took the reference point as Earth's surface, where the potential energy was assumed 0. However, a more rational choice would be to have a reference configuration where at r equal to infinity, the potential energy should be assumed 0. And why should that be considered rational? So the reason is that since the gravitational force becomes 0 at infinite separation, this fact makes it a more natural baseline. So make this important observation that while it is 0 here at infinity, and this expression actually goes up as the separation r reduces, the negative sign in this formula ensures that the potential energy becomes less as the separation reduces. That is, as it becomes more negative, the potential energy becomes smaller. So many students find this idea confusing, but if you understand that in both the models, whether we take the potential energy as 0 at the Earth's surface or at infinity, both describe the same exact physical reality. That is, the energy decreases as an object moves closer to Earth. The only difference is in the numbers. And that's just because we've chosen different 0 points for potential energy, one at the surface and the other way out at infinity. But here's the key part. The change in energy, that is delta U, is the same in both cases. So if an object falls from a height h1 to h2, the energy it loses is exactly the same, no matter which reference point you started from. So let us run with this convention that the potential energy is 0 at infinity, and as the separation reduces, the potential energy also reduces. Now, this understanding also reflects the fact that energy would need to be supplied or added to the system to separate them back out to infinity. Just like climbing out of a deep well requires work. So as an example, let us say you have a 100 kilogram rocket 100 kilometers above the Earth. Its potential energy, I calculated, would be about 6.2 billion joules or minus 6.2 billion joules. Now, if we add 1 billion joules of energy by pushing it up by an external force, U becomes minus 5.2 billion joules. And we see the rocket moves farther out. Add another billion joules and U becomes minus 4.2 billion. indicating even greater separation. And if you continue this way, adding a total of 6.2 billion joules, the potential energy reaches zero, and the rocket is now infinitely far and free from Earth's gravity. So the next step in the derivation of this expression would be to find the work done on the ball by the gravitational force if the ball were to move from point Q to an infinite distance from Earth, that is our reference point. So remember, the ball is moving up because of an external force that is doing positive work. But since the gravitational force is in the opposite direction, it is doing negative work. Okay, now to find the work done, we of course need to know this force acting on the ball. But here we can see that the gravitational force F is a variable force because its magnitude changes with r, and therefore we need to use integral calculus to sum up the tiny bits of work done over each small step in the ball's outward path. So let us say that at some point of time the ball is at a distance r from the center and moves a very small distance dr. Then we can say that the work done can be written as a dot product of force acting on it during this movement and the displacement dr, which equals F into dr into cos of the angle between them. That we can clearly see is 180 degrees. So when we put this angle and the expression for F as this, what we find is that the work done is gmm upon r square dr cos 180, which equals minus gmm upon r square times dr. And now we can integrate both sides between capital R and infinity to get work done as equal to minus gmm integral 1 upon r square dr as r changes from capital R to infinity. And when you simplify this, what you get is work done W is equal to minus gmm upon r. So this expression we've just derived is a work done by gravitational force to move the ball from point Q at distance r to infinity. Now, we also know that change in potential energy is equal to the negative of the work done. So here, the potential energy is changing from U at a distance r, that is the initial value, to U at infinity, or the final value. So we go ahead and write delta U as U infinity minus U is equal to minus W. And when we put 0 here, what we find is that U, the potential energy of the system at this separation R, is equal to W, or minus gmm upon r. Now capital R is very often associated with the radius of the Earth, so we'll take small r, which is a little more general form, and express this formula as U is equal to minus g capital M into small m upon r. And I would urge you not to see it as just a formula, but as a map. It tells you that when you are standing on Earth, you're not at zero energy configuration, because zero is out there at infinity. You're actually at the bottom of a gravitational well, because U at this point is most negative. This also reflects the bound state. More negative potential energy indicates a more tightly bound system, and therefore the more energy it takes to separate them. So if you like this lesson, give it a thumbs up, that'll be helpful. And if you want to learn more about this topic, including Kepler's law, Newton's law of gravitation, I would suggest you head over to this playlist, and I will see you in the next lesson.